Hi viewers, welcome to all. Here we are discussing about a project algorithm level error detections in low voltage systolic array. In this research, a strategy for achieving energy saving via decreased voltage operations is suggested by incorporating algorithm based fault tolerance error detection, okay, ABFT method into a digital architecture. The solution identify timing issues using a systolic array matrix multiplication running at decreased voltage and identifying fault on the fly to prevent energy intensive memory round trip. This method has been developed. To design the proposed work of this paper presents a matrix multiplication using checksum based error detections at two different modes using array multiplier. It's configured with a conventional and reversible logic full adder for area, delay and power reduction. The mode 1 considered as bit mode. This will design using 4 cross 4 matrix multiplications and detect the error using checksum method. Okay, the mode 2 is a vector mode. This mode will design using 4 cross 4 matrix multiplications. In the systolic array of processing element, we have used a array multiplier with a conventional and reversible logic method to detect the error using checksum. Okay, so this method was developed using Verla HDL and synthesized on Xilinx Vertex 5 FPGA and compared all the parameters in terms of area, delay and power. Now we can verify the best paper. So this is a best paper title. So here what they are telling means, here they are telling the matrix multiplication. That matrix multiplications will require the error detection. Okay, so that purpose they are used as a checksum method. Okay, so here they are doing as a checksum based fault error detections. That concept is a ABFT method. Okay, algorithm based fault tolerance. Okay, so here in the matrix multiplication they are designed with a systolic array structure. Okay, so here figure 2 shows the checksum row and column help to detect the errors. Okay, and figure 3 shows the proposed systolic array structure integrating ABFT method. Okay, so here they are developed this work in HSPICE, but we are developed this work in Verla HDL using Xilinx synthesis. Okay, here they have developed this work at 32 cross 32 matrix and 128 cross 128 matrix. This is a bit mode matrix. Okay, so here 32 cross 32 and 128 cross 128 we can possible to design, but it will take a more time and more cost. Okay, for the purpose the low cost project, so here we have developed this code in 4 cross 4 matrix level but modified with the proposed architecture using vector mode. Okay, so we are consider this A11 A12. Okay, this each matrix, right, each pixels. Okay, this is considered as a vector mode. Okay, that means then the existing method they are consider this A11 as a bit. Okay, so here we have considered this A11 as a vector. Okay, that means it's a 8-bit. Okay, so based upon this proposed multiplication we are used as a array multiplier. That array multiplier full adder also used with a conventional and reversible logic method for area and power delay reduction. Okay, now we can verify the outputs. Okay, this is the first part. Okay, is a bit mode. Okay, so this is a bit mode coding. Okay, so test bench. Okay, so here we are given the input A0 to A15. Okay, and the second input is B0 to B15 and X0 to X3 and Y0 to Y3 and C0 to C24 is the output. Okay, so why? Because here we are used as a 4 cross 4, right? So 4 cross 4 means so 0 1 2 3 up to 16 bits we are needed. Okay, after that we need to consider this checksum value is x0 x1 x2 x3 and this b checksum value is y0 y1 y2 y3. Okay, for that purpose we have multiplied this and we will get a 24-bit output. Okay, so 24 values. So here this is a bitwise method. Okay, so here we are forcing the input using data register A and data register B. So this all the things we are register with single bit only. Okay, so this is a top level block. Okay, so here we are given this A zeros and number of B zeros and C zeros given to systolic array architecture. So here we are not directly designed the processing element. So here we are design the systolic array architecture. Inside of the systolic array architecture, we can design as a processing element architecture. Okay, so here we have design of 4x4 systolic array architecture, and we have taken the outputs and it will be given into the ABFT error detections method. Okay, so here this is a simulation for this bitwise method. Okay, so here the first thing we have put a error detections, and second is the input, and third is the output. Okay, so by the error. Okay, so this is a row based error and this is a column based error. So in the paper they are used with the systolic array architecture. So they are using the XOR gate operation for ABET error detections. Okay, so they are summing all the rows of systolic array and it will be XORed with the final processing element. Okay, the same method only we are handled, but they are taken only row based error detections. In the row based error detections, we can't possible to detect this C22. Okay, that means a row and column based thing. Okay, for that purpose we have designed the another one XOR gate for column based error detections also. Okay, so here that's why we are given the error rows and error columns. Okay, so here 0 to 4, here 0 to 4, that means 5 cross 5. Okay, here you can check this is a 5 cross 5 output. Okay, so 0 1 2 3 4 and 0 1 2 3 4. Okay, so here we will given this with error. So here error will occur in error 3 and this error also 3, but it will occur in row and column. Okay, so why means we need to create a manual error here. Okay, so in the systolic array architectures we are creating the manual error here. Okay, so this is a generic based architecture. Based upon this generic value changes, the error will create automatically. Okay, so if I give 0, okay, now you can check the error is zeros. Okay, so error 0 1 2 3 and column based error 0 1 2 3, you can check all the things will be 0. Okay, so if I need to create the error in the first row, okay, now I given 1. Okay, so error will occur in the row 1 and column 3. Okay, and we can check the other codes. Okay, so this is a ABFT 4x4 matrix systolic array vector mode. Okay, so this is a vector mode. Okay, so vector mode means it's a array based multiplications we have used in the systolic array architecture, but in the array multiplier we are used with the conventional full adders and conventional half adders. Okay, so this simulation we can show it on here. Okay, so this things also given in the error rows and error columns. Okay, so here you can check the vector mode. So vector mode means A0 to A15. Okay, consider as a 8-bit. Okay, so this is a 8-bit vector. Okay, so here in the matrix values we can check it on here. Okay, so here this is the output. Okay, so here what is the problem means here input we are given 8-bit, right? So 8 into 8 multiplication process we will get a 16-bit output. Okay, for the purpose the C0s and C24, so it will come up with the 16-bit output. Okay, and the next one is a vector mode reversible logic. Okay, so here the array multipliers we are used with the reversible logic using Priest gate method. Okay, so this is a Priest gate method, so full adder Priest gate. Okay, so this Priest gate method we have used with this paper. Okay, high performance array multiplier using reversible logic structure. Okay, so we are used reference and we have written the same architecture in the paper. Okay, and this all things we are synthesized in Silence Vertex for FPGA. This is the first one, bit mode. Okay, you can check the LUTs, occupied slices, IO base. Okay, and you can check the delay. Okay, 5.376. Okay, and second thing is a vector mode. Okay, you can check with the LUTs and occupied slices and IO base. Okay, and third thing is a vector mode reversible logic. Okay, here you can check the LUTs, occupied slices and IO base. Okay, now can show the RTL schematic. Okay, so this is a bit mode architecture, RTL schematic. So here it's come up with ABFT error detections. Okay, it will generate the errors. Okay, and this is a systolic array ABFT method. It will come up with the processing elements. Okay, so this processing element will consider as a multiplication, and this is a addition process. Okay, and the vector mode RTL schematic is okay, this one. Okay, so here this is a ABFT error detections, and this is the systolic array. Okay, so here in the systolic array we have used as the array multiplications and XOR based addition. Okay, so this array multiplication we are used with the number of half adders and full adders. Okay, it's a conventional method. And the next one is the reversible mode. So this mode, the array multiplier we are used with the reversible logic method. Okay, for area and power election. Okay, so here we can show the any one of the method. Okay, so this is the array multiplier. Here we are used with the full adder pre-gate. Okay, so pre-gate based architecture. Okay, so this all comparisons we are updated in the comparisons document, the comparisons of algorithm level error detections in systolic array. Okay, with using 4x4 single bit mode, 4x4 8-bit vector mode using array multiplier conventional, and 4x4 8-bit vector mode using array multiplier reversible logic gate. Okay, here the area, delay and power will be reduced. Okay, and this is a analysis chart. Okay, and we are written abstract document for this project. So base paper abstract, enhancement of this project, proposed title, proposed abstract, existing system, disadvantages, and proposed system, related notes, literature survey, finally references. Okay, thank you.
If you need more video related with VLSI projects implementation, please like and subscribe this channel.